Hello everyone. First of all, I would like to thank you for accepting my paper to the 14th International Conference on Soft Computing and Pattern Recognition. The title of the paper is Comparative Hybrid Deep Convolutional Learning Framework with Transfer Learning for Diagnosis of Lung Cancer. This paper is written by me, Sajad Dadgar, and Dr. Mehdi Neshat. Lung cancer stands as the most common type of cancer in men and has second rank in women worldwide. Moreover, lung cancer, because of the risk factors that affect respiratory system and its mortality rate, is the most lethal type of cancer. In general, there are two types of lung cancer, small cell lung carcinoma and non-small cell lung carcinoma, that also divides into three categories depends on the location, shape, and the size of the nodule. Since each category and these lung cancer types has different treatment, the diagnosing and detection of lung cancer in the early stage of the cancer is crucial. To diagnose lung cancer, the first step is to use imaging tools such as CT scans that help us to monitor diagnosed cases effectively and discover nodule and cancer characteristics better. However, diagnosing and detection of lung cancer just by observing CT scan images is very time-consuming and challenging because nodule, especially in the early stage of cancer, is they are very similar to each other, and it's hard and difficult to distinguish them. Therefore, computer-aided diagnosis systems, by employing machine learning and deep learning techniques, are able to overcome these problems and classify each type of lung cancer with high accuracy and in a short amount of time. In this work, since we are going to use CT scans, which is a visual data, we focus on convolutional neural networks due to their ability to process visual information. In more details, in this work, we propose a comparative hybrid convolutional deep transfer learning model including 6 state-of-the-art CNN-based architecture to detect 3 widespread lung cancer types. Furthermore, we extend this pre-trained model by adding different layers and develop 5 distinctive architectures to deal with the overfitting issues. And finally, we discuss and analyze hyperparameters and their impact on the classification and model training. Before discussing methods, in this work, we use chest CT scan images dataset that contains 1000 CT scan images. As you can see in this figure, this dataset has 4 different classes, including normal samples, squamous cell carcinoma, large cell carcinoma, and adenocarcinoma. This dataset is publicly available in this link in the Kaggle. In the methods section, for fine-tuning the pre-trained model based on the dataset, in the first step, we applied resizing, rotation, flipping, and shifting for pre-processing and data augmentation. Next, we use 6 CNN-based pre-trained models that earlier have shown a great performance in image classification, including VGG16, ResNet 152v2, MobileNet v3 Small, MobileNet v3 Large, Inception ResNet v2, and finally EfficientNet v2. Followed by these models, we further try to extend the networks and build 5 different architectures for each pre-trained model. As shown in this figure, from the simplest to the deepest architecture, we add dropout, batch normalization, and fully connected layer to our network. For example, in the first and simplest architecture, we have a pre-trained model followed by a dropout, flattening layer, and a 4-unit dense layer to classify normal cases and 3 lung cancer types. In the second architecture, we add in batch normalization and a ReLU activation function. In the third architecture, we add an additional batch normalization and fully connected layer. In the fourth architecture, we try to add a batch normalization, dropout, and fully connected layer. And finally, in the last architecture, we add another batch normalization, dropout, and fully connected layer in our networks. Since we have a small dataset and we may have overfitting problem in the model training, by developing different models, we try to find a model that perform well on training and also in the test sets. Although all CNN-based pre-trained models used in this paper have shown great performance in the image classification task, by fine-tuning the model with the dataset, we found that the inception result is the best performed model among all CNN models. Inception ResNet is formulated as a combination of the inception architecture with a residual connection that allow this model to benefit from both networks, such as avoiding the vanishing gradient problem by skipping some layers due to the use of the residual models, and take advantage of multiply size kernels in a single layer that enable the networks to extract patterns with different scales for using the inception networks. As you can see in this figure, Inception ResNet V2 has many blocks called SM, Inception Reset A, B, and C, Reduction A and B. That in each block, ResNet and Inception structure are embedded in the network that help this model to extract important features from visual information, which is the CT scan images in this task. Regarding experimental results of our model, the average training loss for proposed hybrid CNN models with 5 various structures can be seen in this figure. In the figure, Model 1 represents CNN with the simplest architecture, and Model 5 is the deepest architecture. As you can see in the figure, except VG16 and MobileNet V3 small, the most effective architecture for training was Model 3 that converged rapidly and considerably minimized the loss function. Moreover, as we discussed earlier, the result of the Inception Resonant V2 was much better than other models, and the Model 3 of this architecture has the best performance by achieving 91.1% accuracy, 84.9% precision, 79% recall, and 81.5% F1 score. Moreover, as hyperparameters play a significant role in improving the performance of classifier, we consider the impact of batch sizes and learning rate in the best performed model. This figure shows the accuracy of the proposed model with 4 different batch sizes as 8, 16, 32, and 64. As you can see in the figure, the average performance of models with small batch sizes was better than the large sizes. Regarding learning rate, we tested 3 various fixed value and a decay strategy for the learning rate. Obviously, the decay learning rate method performed considerably better in the term of accuracy of cancer detection. Finally, to conclude our work, we developed a hybrid model consisting of 6 CNN pre-trained models with fully connected, dropout, and batch normalization layer to classify 3 different lung cancer from normal cases. Further, we evaluated and compared the effectiveness of proposed hybrid model with different state-of-the-art CNN models. Next, we considered and analyzed the impact of batch size and learning rate in the best performed model to illustrate the hyperparameters and their significant role in improving the performance of classifiers. And finally, we showed that Inception Resonant V2 with transfer learning could outperform other hybrid models. Also, all implementation of our model can be found in this GitHub link. Finally, thank you for your attention, and I hope you find this presentation informative.